Hi Rockridge, this is Mrs. Berger, and today we will be discussing the last of the new material for our unit, solving nonlinear systems. So if you recall, a system is basically a set of two different equations. Back in the day when you were in Algebra 1, you might have seen a system that had y equals 2x minus 1 and maybe y equals negative 3x, right? And it was a system because it was two lines instead of one. And if you recall, the solution to that system was a coordinate pair located exactly where they cross one another. Those are the solutions to systems. So we will graduate from lines today, and we will go beyond that to quadratics and other types of polynomials in these systems. But still, you've got basically a system with more than one equation. That's what a system is. A system of nonlinear equations is when one of the equations, at least one of them, is not a line. Okay? So solving these nonlinear systems by graphing, same concept. We still find the solutions where they cross each other. And that's important to note, where they cross each other, okay, not the x-axis. So that's sometimes confusing. And remember, the solutions to a quadratic all by itself, the solutions were found at the x-axis. When you have the solutions to a system, it's where they cross each other. So be careful with that. The solution to a system is where the functions cross each other. The solution to a simple quadratic or any polynomial function of itself is where it crosses the x-axis. So for instance, if we look from left to right on these graphics, the first set of a parabola and line have no solutions because they don't cross each other anywhere. The second parabola and line has one solution at the one location that they cross each other, and of course this particular line and parabola cross in two places, so they have two solutions. And again, those solutions are an ordered pair, an xy pair. Let's look at these graphs. You might want to pause the video, and why don't you pause the video and jot down the coordinates of where you think these cross each other to document the systems. I'll do the same. So pause the video and document your answers. Alright, hopefully you've had a chance to take a look at that. Notice that it is where they cross one another. You know, the coordinates of number 3 aren't perfect. It's approximately 3/2 or 1.5 there. Alright, so that's fairly easy peasy. Let's take a look at when we are given the functions in a set like this. So here is a system here. Here is a system here. We'll want to graph these and find the solutions by hand. Let's remember how to graph these. This first one is a parabola. This second one is a line. Obviously, to graph the line, we would prefer to see it in y equals mx plus b form. Just for fun, let's graph that. That's the easiest, obviously. So we know that it crosses at -2. It has a slope of 1. So we might as well just graph that first. It's the easiest. So there's that line. And now we'll graph the parabola. The parabola is given to us in standard form, so try to recall, how do you start graphing a parabola in standard form? Hopefully you're thinking and you remembered that -b/2a will get us the vertex. So for us, -b/2a is -2 over 2 times 1, which is 2 over 2, which is 1. So our vertex can be found at 1 comma something. To get the something, the y coordinate of the vertex, we replace the x's with 1's. So 1 squared minus 2 times 1 minus 6, we're at -7. So my vertex of this parabola is at 1, -7, right there. And there's a couple of different ways that you can get the rest of the points on this parabola. You can remember the key points and just keep expanding out. Our leading coefficient is 1 on this. Also, you could put in points. You could enter an input of +2 On the x, you could enter that up top into the equation, and once you put positive 2 in for x, you could see what happens with y. You can build yourself a little table of values. And of course, as always, we can put this into our calculator and ask for a table of values there as well. So let's graph this parabola, and it goes up here. So one place we know that this crosses is at -1, -3, so that's one solution. But then we know that this continues up here, so we'll need to continue inputting values into our function. So if we were to put in, let's see, this was a +3. If we were to put in +4, let's see if that is where this one crosses here. So if we put in +4 for x, if we put in 4 for x, a y would be 16 minus 8 minus 6, so it would be 2. So 1, 2, 3, 4, 2. Sure enough, that's another place that we cross. Okay, so our two solutions are -1, -3, and 4, 2. And always remember, when you are inputting your final answer, it should be a set of points. It should be a coordinate pair. Alright, the next system we have is actually two different parabolas. We have two parabolas on this one, so it's not a parabola and a line, which is fine. We know what to do with these. So if we graph the first one in red, we know that that's in intercept form, so we know this parabola must be crossing at -2 and -6. That's where it's crossing. We know it's got a positive leading coefficient, so its vertex is somewhere below those 2 points because it's going up on the ends. To find the vertex of this, we find the middle of it. The vertex must be at -4, something. The vertex is at -4, something. To find that something, we replace x with -4. And so we'll have a -2 times a +2, so -4 is where that vertex is. So that's this picture of this parabola right now. We will find out if we need to get a little more specific with those points on the graph in a moment when we graph the other parabola to see what the solution is. So if we graph the other parabola in blue, we'll notice that this one has a vertex at, well, look at that. The vertex is at -4, -4 again. It also has an A of 1, and so it actually follows the same set of points. So the solution to this system of two parabolas is actually an infinite number of solutions. So infinitely many solutions. Now, some of you may have been tempted to write all real numbers as the solution. That is not how we would state the solutions to this, because all real numbers, that would include something over here and something over here and something over here, and clearly those are not solutions to this system of two parabolas. So don't call this all real numbers. However, there are infinitely many solutions, right? Everything along here all the way up to infinity, everything along here is considered a solution. So we couldn't possibly list them all. But don't say that it's all real numbers, because it's not all real numbers for the systems, for the solutions. Okay. All right. Let's make use of our calculator to help this process go a little faster. If you are presented with this system, once again, like two problems ago, this is a line and a parabola. Or I'm sorry, well, not quite a parabola, a sideways parabola. But we will take a look at how to enter this into the calculator. Now, obviously, when you come across our calculator, on the calculator we only have y equals. So we need to make sure that everything is in y equals before we put it in. This first one can be written as y equals 2x minus 3. Just make sure you take your steps to isolate the y and you'll get there. So in our calculator we will be inputting 2x minus 3 as the first one. On the second one, and if you need to pause the video to see how that happened, go ahead and do so. Make sure that you do that work for yourself. On the second one, we need to isolate y again, and so our first step of isolating y for that one will be getting 7x and 3 out of the way. So add 7x to both sides, subtract 3 from both sides. Now notice y is still not by itself. We need to take the square root of y to get it completely by itself. When we do that, we get the square root of 7x minus 3, but always remember when we take an even root, when you impose an even root to isolate something, you will need to do plus and minus. So there are actually 2 more y equals we need to input into our calculator. The square root of 7x minus 3 and the negative square root of 7x minus 3. That is how we will enter this system into our calculator to find the solutions. So go ahead and do that in your calculator in y equals. I'll do that right now as well. Pause the video and we'll come back together to see how to find the solutions. Alright, and now if you'd like to see the graph, you can certainly do so. As you can see, it's a sideways parabola and a line. And of course you can do this on desmos.com/calculator as well. Now we certainly see this crossing right there, the red and the blue are crossing, as well as the black and the blue are crossing. So we can visually see where these are, we just don't know what the actual coordinates of them are. So we're going to ask our calculator, hey, can you help us find that? Our favorite menu on the calculator, second, trace. And as you look at these options, what do you think might help us? Hopefully you're yelling intersect. Yes, we need to know where those intersect. So choose choice 5. And choice 5 brings up this question, first curve, question mark. What it's saying is, hey, I need to know what 2 curves you want to know about crossing. In this particular instance, we technically have 3 different curves, so we're going to need to do a pair at a time. So the first curve being the blue line is certainly a fine step to begin with. So the first curve being the blue line, if the cursor is on the blue line as my first curve, I'm fine with that. So I will hit enter. Yes, first curve is the line. Second curve, would you like the second curve to be the red curve? That's fine. I'm actually closer to the black curve, so actually let me jump to the black curve. And when you go between curves, you're going to use your up-down toggle buttons to go between curves. So I'm going to toggle up-down to the black curve, and I see the text below is in black, so I'm on the black curve. Now, notice that my cursor is not actually on the curve, it's to the left of the curve. This isn't going to work until my blinker is actually on the black curve, so I'm going to use my left-right to scoot my toggle along the left of the curve so that I'm actually on the curve and blinking on the curve. So that was toggle up down to go between curves and left right to go along the curve. Alright, once I'm on the second curve and I can see it blinking there, that is the second curve that I want to talk about intersecting. So I hit enter. And then of course my least favorite word in math, guess. Yes, let's guess the intersection there. So there's one intersection. 0.75 and negative 1.5. That's my first solution. So 0.75, negative 1.5, 0.75, comma, negative 1.5 is my first solution. Now, to find the second solution, I will need to start this process again. Second, trace, intersect. And again, it's asking if I like the blue curve. I certainly think that's fine. I need to know where the blue and the red curve. I am going to scoot to the right a little bit to get a little closer to the intersection, just to make sure my calculator doesn't get confused about what I'm asking about. So yes, I'm still on the blue curve. I scooted to the right along the curve, and I'm going to hit enter. Yes, I want that to be my first curve. Now it's asking second curve. Would you like it to be the red one? Yes, that's completely fine. And I can see my cursor blinking so that I know I don't have to scoot along it. So yes, those are in the region of where I want to find the intersection. So yes, I want the red one to be my second. I'll hit enter. And then the next question is guess. Yes, let's go ahead and guess where they're intersecting. It says that intersection point is at 4, 5. So the other solution is 4, 5. Those are my solutions. And remember, I always put them in ordered pairs. Now that we've done this graphically, let's learn how to do it algebraically. There are 2 ways to do this with algebra: substitution or elimination. My first demonstration will be on substitution. You actually did do this in Algebra 1 with the lines, so some of this may bring back memories. On the second one, I will do elimination, so I will demonstrate both. Substitution is actually probably going to be the one you use most often. It's usually the most obvious to use. And the way it works is you isolate one variable in one of the equations. So this looks like a good candidate. I can easily isolate y. I can isolate y by adding x to both sides. Once you have a variable isolated, and it doesn't always have to be y, you could have isolated x. But once you have a variable isolated, you know that y equals this stuff, and so you take this stuff and you replace y in the other equation with it. It's kind of like the transitive property. If y equals x plus 2 in this equation, then y up here must also equal x plus 2. So once we substitute, we are left with x squared plus x plus 2 squared equals 100. Well, how in the world do we solve this? We can solve x. We can solve for x. We have our quadratic tools available to us to solve for x. First, remember that this is x plus 2 times x plus 2. So make sure that you FOIL that together. Okay. So what we have here is this x squared out here all by itself plus x squared plus 4x plus 4 equals 100. Let's get our like terms together and get a 0 on the right. So 2x squared plus 4x, let's subtract 100, so minus 96 equals 0. Now, this is a quadratic that I know how to solve. The first thing I'll do is I will take 2 out, and I'll get down to x squared plus 2x minus 44, I believe. Nope, 48, sorry. 48. And this, I could either throw quadratic formula at it. This actually looks like I could factor it. Multiplies to 48, negative 48, and adds to 2. A positive 8 and a minus 6 is going to take care of that for me. So remember, when we do our quadratic solving, we take each factor and set it equal to 0 and solve. And so that's telling me that x equals negative 8 and x equals 6. But hold on, let's stand back for a second. This was solving a system. Don't I need coordinate pairs when I solve systems? You absolutely do, and you don't have that yet. You have the beginnings of that. So right now, and I love, when I'm finished, when I'm down at this point of this problem, I love just setting up my answer box and getting it started so that I can feel like I've accomplished something. So what I know now is one coordinate pair has an x value of negative 8, and the other coordinate pair has an x value of 6. That's what I know right now. I know the two x values, but I don't know the y values. And some of you are already jumping ahead of me, I know. When you have x values, and you have something beautiful like this, you can easily find the y values, right? So one at a time, enter your x values that you found. Negative 8 plus 2 is a negative 6. So this must go with a negative 6. And then if we were to input 6, 6 plus 2 equals 8, so this must go with an 8. That's the last part of our solution. So don't stop here. Okay, make a note to yourself, don't stop here. That is not the final answer. It certainly was a ton of work to get there. I don't disagree. That is a ton of work to get there. But that is not the solution to your system. It's not a solution until you have your coordinate pairs. Okay? Alright, I'm going to clear the board now. If you need to pause and look at that for a little while, do so. I am going to demonstrate elimination now. Elimination is actually not a whole lot harder or more or easier than the other method of substitution. It just acts a little differently on your first step. Elimination is used when you can eliminate an entire variable, either x or y, by adding the two functions together. This one is set up just beautifully for that to be done. If we were to add these top to bottom, we would have the x's completely disappear or get eliminated. So y plus y is 2y, x squared minus x squared is 0, negative 6x plus 6x is 0, 14 minus 4 is 10. And so therefore y equals 5. So I actually only have one solution on this guy, and the y coordinate is 5. If I want to know the x coordinate, I will go ahead and take that and choose either function. It really doesn't matter which. Neither one looks any prettier than the other. So I'm going to take this one. I'm going to say y is 5 equals x squared minus 6x plus 14. This looks like another quadratic I'm going to need to solve. And so let's get everything together. X squared minus 6x, let's subtract 5 from both sides. And then hopefully we can factor this instead of having to use the quadratic formula. Multiplies to 9 and adds to negative 6. Hopefully you're screaming at the video, minus 3 and minus 3. And so we actually have a double root at positive 3. And so 3 comma 5 is our solution to this. That was using elimination. You definitely could have used substitution in that problem. You could have said, hey, y equals all of this. I'm going to substitute it up here. You will actually end up with the same first line of work down here. You'll actually have the same you'll end up doing the same factoring work. And then you'll back into the y, okay? So one is not better than the other. It's really just when you come upon the problem, which one looks more obvious to you. If I look at our last example here, absolutely, you can substitute this, since y is all by itself already, nobody has to do any work, you can substitute this in down here for y. You could also use elimination in order to eliminate. Now you can't eliminate the x's, there's just no way to eliminate the x's. But if you were to make one of these negative, let's make the top one negative. If you were to make the top negative, you could eliminate the y's, okay? So for those of you that are doing substitution, you can certainly use the next few minutes to substitute this in here. I'm going to demonstrate both methods here. I am going to make the top negative for those that are doing elimination. For those that are doing elimination, you'll have negative y equals negative 4x minus 2, and then below that you'll have y equals x squared plus x minus 8. The y's get eliminated. X squared minus 3x minus 10 is what you'll have to solve. If you were to factor this, 5 and 2 get you what you need, and x equals 5 and x equals negative 2. And then you're off to the races, right? You can set up your chart with the x values of 5 and negative 2, and you can plug those back in. Let me go back over to the substitution folks and demonstrate that for you. So for the substitution people, this is that work. I am going to substitute this down here for this. 4x plus 2 equals x squared plus x minus 8. Get all your terms on one side because it looks like I'm going to have to solve a quadratic. Nope, it's minus 10. Minus 10 equals 0. And just like the elimination people, we have a quadratic that we need to factor, and it's the same factors, x minus 5 and x plus 2. So once again, it really doesn't matter which one, it's just, what do you see? When you come upon the problem, what do you see you can do the easiest? Let's finish this out for both sets of folks. So if you came up with x values of 5 and negative 2, set those up in your answer table. I highly recommend that at this point, just so you don't get lost. Don't stop here, okay? Right next to that x equals 5, comma negative 2, please write. Do not stop here, okay? Now, let's put these into the original. So y equals 4 times 5 plus 2. That's our first one. So this must go with a 22. And then y equals 4 times negative 2 plus 2. So that's negative 8 plus 2 is negative 6. So that's our answer there. And since we already built our answer box, we're pretty much done once we put those in there, okay? So that is the last of that day. That's the last of the unit. You'll have a quiz and then a test on this. Let us know if you have any questions on the homework, and please make sure you try all the different types of problems.